Good evening, everyone. Thank you for letting us know presenting the VIVET therapeutics. So we maybe the last one. We effectively pretty recent. The company was really funded in I would say we started in November, but officially most of the people were having two jobs at the same time, and we were able actually to make the announcement in early April of 2017. So who are we basically? So we are a group of, the team is really extended to a high level of competencies in the field of gene therapy. We have Gloria Gonzalez, our Chief Scientific Officer, working in Spain, in Barcelona specifically. Maybe I should be slightly far from the microphone. And she has an extensive experience in the field, working in Spain for more than 20 years, also working in the New York team. And Jens Kurt, our Chief Development Officer, is coming from Novartis and Anokion, where he worked a lot in terms of technological and operations and development. We also have Bernard Benichou, our Chief Medical Officer, who's been at Genzyme before, working in the field of orphan therapies and metabolic disorders. And Suzanne, as part of the General Counsel and Finance, a lot of experience in deal, because we're doing a lot of different deals. And also as handling the merger and acquisition, so a very significant experience for our future. Personally, I'm coming from Gene Biology as the Chief Operating Officer, been in pharma for more than 25 years now. What is gene therapy? I'm sorry for some of you, it may sound like a very basic slides basically, but I think it was important to remind that once you have identified a gene, and more specifically in monogenic disorders, well, this is a main actually target you can have, and an easy way to transfer a therapeutic gene. You put that gene in a vector, it's like a car basically. You're going to inject this vector, and the construct around the car is very specific. There's promoter, you have specific capsids, specific sequences that will clearly help the gene to be expressed by the mRNA, to express the protein in the right cells and the right target organ with the right concentration eventually. Then you manufacture, and that's part of the key asset. You inject to the patients. The viral vector will target the nucleus of the cells. Well, it will not integrate the genome of the body, but actually express systematically and consistently the protein that will actually deliver as therapeutic. So what we call the AAV is a kind of a cargo where we put a lot of construct and a lot of knowledge and science, and that means there's a lot of being able to cure the therapy. That's the objectives. So what does the gene therapy landscape looks like? If you look at this kind of bull's eyes representation, you can see actually what I would call a gap opportunity in the middle. And this is where all these fields from the metabolic, there's a pointer maybe here, from the metabolic and neuromuscular disorders, the VIVET we're located here basically, but I can show you. There's more than 50 companies in immuno-oncology, but that's a different kind of cell therapy. More neurology, a lot of gene therapy companies. In ophthalmology, it's highly present and represented. Immune deficit and blood disorders, which is going to come very soon on the market, we hope, and also in ophthalmology with Sparks. But with all of these companies in gene therapy, there's a lot of knowledge that's been gathered and a lot of improvement. We know there's a lot to come, but if you think about this, more than 50 companies, there's 5 in pivotal today, there's probably 5 on the market. Gilead has been really recently approved, but it's more cell therapy, but Sparks in ophthalmology has been will be clearly approved in the US very soon. So that's really changing, and this gap opportunity will really lead to a lot of different companies coming. So there's more knowledge, more know-how, more capabilities, and more experience in the field. And it really comes through as a market reality now. We know there's a lot to build around the pricing, but that would be another debate at some point. So why were we interested in the field of metabolic disorders? If you really look in the mapping of the inherited liver diseases, it's a group of very extensive metabolic disorders, and most are due to a very specific defect, highly identified either through newborn screening or type of registries that alter the metabolic pathway and lead to very severe consequences from, I would say, very debilitating disorders to death for the patients. What is important is that 50% of the people who are affected by rare diseases are children. And children under the age of 18 can represent up to 12.5%, for example, in the US, of liver transplantation. So as a concept, if you do if you can cure with liver transplantation, it means if you can change the gene inside the liver and really replace the functionality, you really do like a phenotypical cure, basically, so you can actually cure the disease by itself. So if you look at this series of adult liver transplantation, or if you look at the children here, if you take the focus on the Wilson disease, it's more than almost 19% of the liver transplantation. And if you look at the children, it's about 10%. You will see other disease here, like PFIC, I will describe later. But it's typically disorder when you can actually replace the functionality of the gene inside the liver. So we base the company around different assets, and what we need on top of it is the know-how, the knowledge, and the capabilities. So what we actually build the company is around an exclusive research collaboration with the CIMA. CIMA is a Center of Investigation of Applied Medicine in Spain, in Pamplona. We also have a license on a very dedicated and specific vector. It's a new vector, and this vector has this ability to be able to reach the liver specifically with a high level of transduction and some know-how around the manufacturing. And also we know that we have to go around this sustainability of expression and immune response. So kind of a triangle, I would call it a virtuous triangle. If you can handle the immune response, you can actually maybe improve the sustainability of expression, but also you can actually target children. Because children will have the liver size, which will actually continue to grow, but you have to keep the sustainability of expression, which is adult. Today, in hemophilia, for example, they have up to 7 years follow-up in terms of expression. And I think in ophthalmology it's the same, it's about 7 years in human, but 12 years in the dog. So that means it's sustainable and it provides a real efficacy. We're not a manufacturing company, but we rely on very specific partnership, really solid partnership and experienced company. We do the same for the improvement in terms of non-clinical development. But more importantly, what we try to do at the beginning is to really understand the famous 3 Ps, the physicians, the payers, and the patients. This is the other virtual triangle we need to understand to where we go, what do we need to provide, and I'll do a focus on the Wilson disease. So the big players going with us and the investors are Novartis Venture Fund, Roche Venture, Elscap, KURMA partner of course, Ethos and Columbus, and they're really committed and providing a lot of support on all around this gene therapy environment, which is pretty complex, it's very dynamic, it changes every day, and that's a very stimulating area for most of us. So the primary indication we're having is Wilson disease. So what is Wilson disease? Wilson disease is a disorder where the main unmet needs are coming from hepatic symptoms and neurological. It's pretty simple. It's a deficiency in a cell. It's a deficiency in the cell protein, in a transporter protein that you cannot eliminate the copper. So if you don't treat the disease, if you get very badly diagnosed, don't treat the disease, it's a deadly disease. You go for liver transplantation if you're lucky in the next 2 weeks, otherwise it's a deadly disease. So you have to treat the patient as early as possible. So the main issue today, as you can treat the disease, you can eventually stabilize some of the patient, but you still have a kind of continuous evolution of the disease because 20 to 50% of the patient have very severe neurological outcomes and symptoms. The side effects of the drug are pretty important, lead to 10 to 40% of lack of compliance. At the end of the day, up to 50% of the patient are non-compliant. And we know that up to 15% of the patient will go to liver transplantations. And we have one organ actually to transduce, which is the liver, and that's why we need a really dedicated AAV that goes specifically in the liver. In more details, when we talk about hepatic, it's a very elevated liver enzymes approach issues and neurological, which can be irreversible, especially at the initiation of the treatment. And this initiation of the treatment can be extremely deleterious for the patients. So the earlier we can diagnose, the earlier we can control the disease, the better we can actually focus on the patient's profile. And this is what is very important in gene therapies. Which patient are you going to focus first? You can't treat any patients as a whole. So what we discussed with the KOL, and we try to get their impression and the optimal strategy we can have, is not only they have an excellent receptiveness of the disease, but mostly they clearly identify the notion that if we can focus on the stabilized patient at some point, even mild cognitive impaired patients, that could be the famous phenotypical cure we can have with the patients. Then we can actually go for patients with even some more hepatic symptoms without, of course, liver transplantation or cirrhosis. And I will actually expand the stratification of the patients. And then we can focus on more pediatric and mild to eventually moderate neurological patients. And the last group will be the one with severe patients. Because what we know from the liver transplantation is that it cures the disease and it reverses the neurological outcome. And that's pretty significant. So what we have today is we have a very significant construct, and we are able to identify the gene therapy candidates clearly showing a reduction in the accumulation of the copper in the mice knockout model. We've also been able to optimize this mini gene in terms of potency. We've shown very superior efficacy compared to what we call the wild type, the normal gene we have. So that's why we optimized it. And we also demonstrated superior efficacy in advanced disease stage, because the disease progress over time, so you may have to treat different kind of patient with different kind of liver insufficiency or liver accumulation of copper. And we've shown that in improving the liver histology with a good safety profile. So at the whole, we've been able to get the orphan drug designation in Europe and US. With the manufacturing and regulatory discussion, we can reach the IND and CTA by the end of 2018. But we're also working on other diseases where liver transplantation can cure the patients. And at the end of the day, for example, for this progressive familial intrahepatic cholestasis, which is a deficiency in transporters of the bile, there's only one option before the age of 20 years old is to get liver transplantation, or the patient will die actually. But that will be young patients, and also for type 3 and citrullinemia and other diseases with newborn screening and neurological outcome. On top of that, we know that we need some immune response modulation and sustainability of expression. So we have some platform partnering here. We're not giving too much detail, but we know we have to combine these three assets for the visual triangle of developing these drugs. So thank you for your attention.